Good morning, everyone. My name is Erin, and I am the Event Assistant at SMTA. I would like to thank you all for attending this SMTA online presentation, and I will begin today's session by introducing our instructor and topic. Today's featured speaker is Ray Prasad from Ray Prasad Consultancy Group, who will be presenting Design and Assembly Process Challenges for Bottom Terminations Components, such as QFN, DFN, and MLF in tin, lead, and lead-free world. For those of you who aren't familiar, the SMTA offers numerous benefits to its members for networking and learning opportunities, such as access to free PDF downloads of full-length technical articles from the knowledge base, member rates on educational programs, job postings, and much more. All details regarding SMTA activities can be found by visiting the SMTA website at smta.org. Before we start, and as a formal note, please consider the following copyright statement. Copyright laws protect all presentation materials. Any unauthorized use outside of the context of this presentation is strictly prohibited. The presenter has indicated his preference to answer questions throughout the presentation. Please send your questions to me via the question box on your screen at any time during the broadcast, and I'll read them aloud at the conclusion of each section. And with that, I'll turn the presentation over to you, Ray. Thank you again to everyone for being with us today.
Thank you, Erin, and thank you all. And we can just get started. Like Erin said, I'm Ray Prasad, and I hope you can see slide 1. And once in a while, since I can't see your faces, I'll mention what slide we are on. And so we are on slide 1 here. This is a presentation that we have this week, and same time, same place next week. All right. In slide 2, basically has Erin, okay. This is slide 2, basically a very quick background. Before I got started consulting and teaching, I have been doing this for about 18 years or so. I worked for Boeing and Intel and set up SMT in those companies, in the 80s and early 90s. I have been very deeply involved with IPC. I chair this BGA committee 7095, and the other committee is 7093. That's the BTC, Bottom Termination Component Committee. These are the two committees that I chair at this moment, and I have chaired many other ones like package cracking, design, land pattern, and so on in the past. With that, there is I've written a couple of books and so on, so I've been involved in industry for a while. On slide 3, this is based on the 7093 that I said that I co-chair with my colleague, based on the book and so on. And with that, we'll get on to this outline of this class on slide 4. So what we are going to do today in this hour and a half or so that we have, and I'll allow enough time for you to ask questions. And as Erin mentioned, if you have some question as I'm going along, you just send her a message, and she will stop me in between when she thinks it's appropriate time, and I'll answer that question before moving on. Because sometimes it's better to address those if you have any question right then than at the very end, because you may have forgotten by that time. So in any event, there are essentially what we'll do today is talk about introduction of BTC. There are various types of them, and just briefly discuss how the BTC package is made. Understanding of that is kind of important so that you know that what kind of issues you can expect and what kind of problems the package itself causes. And then we'll talk about things that has to do with the design of the BTC, using the BTC design on the board. So land pattern design, laminate considerations, those kinds of stuff. Component issues, and surface finish. Next week, we will basically focus on manufacturing issues. So this week is an introduction and design. Next week is manufacturing assembly process guidelines, with a specific focus on printing and reflow process, reliability requirement, quality requirements, rework, and those kinds of things, and conclude that with some general thoughts about how to make sure that we don't have problems controlling quality. So let's get started. On slide 5, just a general theme here that the SMT has been in high volume manufacturing for the last more than 2 decades, and like 1985, I would say, from high volume manufacturing perspective, and I have been working on it since a little before then, but that's when IBM came out with the 286AT. That was a very fast computer, 6 megahertz. In any event, even though after all these long high volume experience, in general, very few companies have very high yield. So less than 10% of the companies have the first pass yield of 90%. That means 90% of the companies are doing a lot of rework. And I mean, this is a process that's relatively simple, but if you do it right, then it's simple. But if something goes wrong, this is also a process that produces the scrap at the same high speed. And then we added no clean flux. Then we added, as the time went by, fine pitch devices. Now we are adding these BTCs and bottom termination components with the with the no lead. So you add all those and then add on the lead-free technology. So these things are not making things easier. The old technology is not going away. Even through-hole is not going away. And all these newer things keep coming on the same board. So the problem getting worse, not better. And that's a good thing, because that keeps all our jobs safe. If things were simple and easy, who will need these process engineers? Who will need us? So that's a good thing. Now, what we are focusing on this seminar is the important design and assembly issues, and just focus on useful information, practical information. And this is a relatively new technology. Some parts of it have been done for a while. And the key thing in here, I'll give you examples as we go along, and this was something recent. I'm working with the client on some issues, and we were doing fine with the process they have. And then once you introduce the BTC, we had to change a lot of other stuff just to accommodate BTC. And that was working fine for BTC, but was causing a problem something else. So we made some additional changes. So, and we will talk about those as we go along. The bottom line in here is that you're not going to have a board that just has a BTC and nothing else, and that complicates the problem. So you'll have to sort of have a balance so that everybody's happy, because if there's an open or solid joint defect in any component, doesn't matter what the cause is, this component or that component, we still have a problem. Some of the major challenges on slide 7 is that you have these different needs of these different components. As an example, this is not a seminar about BGA, but in general, you have heard of the head and pillow and those kinds of issues. There are a lot of reasons how to address those. But in general, I think you are better off to have more paste. But if you have more, and that helps the BGAs. In BTC, if you have too much paste, you run into problem of the floating, where the package starts. You end up having a lot of voids. So, that's an issue. In here, in the BTC, we'll see that in a few minutes. The ends of those terminations are basically exposed copper, and that presents a challenge about whether we need the toe fillet, because you really can't get the toe fillet. And some people might want to reject those joints, and if you do, then you have a problem, because you can't really reject them because the way the package is made. So how to deal with that? And then the issues about solder balls, rework, cleaning, inspection, they always add a challenge because we have very tight spacing between the package and the board, and those issues, they are there for other components, but they become more of a problem, especially the cleaning and inspection. And all right. So like I mentioned, that these are not the only, BTCs are not the only components. There are the other packages, BGA and so on. So you have this fine balance about providing the right amount of paste, making sure the joint is reliable, and then making sure that we're not causing opens or floating and too much void in the BGA. In slide 9 here, when it comes to inspection, that's even worse issue. And part of the thing is, at least in BGAs, you can use these endoscopes, and you can attempt to see something in the second, third row underneath the component. BTC, on the other hand, is essentially like a postage stamp, so you can't see anything under there. So, and then you have these fillets, that's exposed copper that's not going to form, so you can't use that as a guideline either, because this is a postage stamp. So how do you go about making sure that you have good connections? So that's those terminations are also called the flanks, and if they're de-wetted, non-wetted, and those are the things that you have to worry about. So the bottom line here is that inspection is really, if you really think about that, it's really not an option for BTC, bottom termination component. It's really not even an option for BGA, but at least you have some capability, some ability to see with endoscopes and so on. And people talk about X-ray as an option. Other than the bridging, you really can't see much else with X-ray. And this 3D X-ray, not everybody has it, and that does work for BGA. For BTC, if there is an open, X-ray will not be much of a help. So when you're getting into these kinds of devices, you basically have to depend on in-process control. What that basically means is that when you get into this technology, you develop the process, have the right design, make sure that, and then cross-section those, do the X-ray, do the cross-section, and go that way, and then see what process recipe, what design recipe is giving you the quality that you need, and that's your best guideline about how to proceed. So I want to emphasize some of the top-level issues here before getting into that. So you have expectation that process control is the way to go. Now, when it comes to process control, everybody thinks it's a good idea. That's not a problem. But there is always a backup of inspection. And the thing in here is that that's really not a backup. You essentially have to be a believer in process control. On slide 10 here, there is a lot of names that are used for BTC, and when I had my first meeting to start this committee, that was a couple of years ago, we spent half a day just to come up with a name, and we wanted to figure out what name will be appropriate so that it covers all these kinds of devices like QFN, quad flat pack, no lead, land grid array, small outline, no lead, SON, PQFN, like that's what Motorola calls their package, plastic quad flat, no lead, micro lead frame package with the, so there is all these different names. So we thought, well, let's just get a name like BTC, and now I believe it has caught on in this last 2 years or so. And so this is the bottom termination. except the BGA, which is also a bottom termination component, but it's not part of this definition. So except BGA, everything else that has those terminations on the bottom is essentially the term that we are using. Slide 11 here, this is the very similar to BGA, but let us move on to the slide 12, which has the same information as 11, but has this picture so we can see what we're talking about. So you have this on slide 12, these terminations, you can see that can be single row, the top picture, and if I just use the arrow, I hope you can see that arrow, that is single row, and then you can have triple rows, you can have double rows, you can have full rows, and in the center you can have a thermal pad, or you don't have to have thermal pad. And if you think about the BGA, I mean, it's essentially the same idea here. It will have a BGA that instead of these flat leads, you just got a ball or many balls. So it's you know, a lot of people call this a poor man's BGA, the BTC, because you don't have to put the ball on. You cut out that process of attaching the ball, and that obviously helps in reducing the price of the package. But this minor difference between not having a ball or having a ball and the rest of the termination essentially the same, it makes a huge difference in everything that we do in the design, in the assembly, in the rework, and so on. All right. Let's move on to slide 13, and what you see here is on the left, and this is the cover that we use on the IPC 7093, and you can see it gives you a sense of size and shapes and color and looks of these various types of the BTC, and new ones are being introduced all the time. So but at least gives you a flavor of what they look like. And on slide 13 here, where I'm pointing my arrow on the top picture to the right, you have the thermal pad and then terminations, and that's one look. The other one could be the one on the bottom, where you have the pads and then center thermal pad. And the one in the middle here basically shows you the lead frame where the outer leads are and the center thermal pad, and you have a silicon that's placed on the thermal pad and wire bonded to these outer leads. So essentially what you have is, think of a sheet of copper, and that's what it is. That's where they started, and I'll become more clear later on. And this understanding is very important. So you have sheet of copper that's etched out, and then that makes the lead and thermal pad. So, and they are now not connected to each other, but this was all one piece of sheet of copper. And then the wire bond is what's connecting all these leads to the silicon. And then once you're done with that, then you just mold it, and there you are. You are done with this package. And if you turn it over like these other pictures, that's just the bare copper that can be plated. Obviously, the bottom side is generally plated with, in case of lead-free, it's without the lead, and in case of tin lead process, it has the lead in there. And that's what reduces the cost, because essentially you have a sheet of copper that has silicon on top of it, and then molding compound, and you're not dealing with the bending of leads, putting of the balls, any of that process steps, and that's why the price is low. All right. So slide 14 has a little bit different looks of those other packages that you have, QFN and so on. Interesting one to see is the one on the bottom right, that sometimes the leads, they can be at a diagonally at the corner. So some packages have that. Now I do want to emphasize that you can see these various configurations, like there is no thermal pad here on the top left. There is a thermal pad on the rest of them that you see here, and the leads can be any shape or format. So there is not one standard how it should be. So essentially, when you're doing a design, you have to look at the data sheet before you do a board design, because you have to match that footprint, as opposed to QFP or PLCC or some other kinds of packages that we have. You know, a QFP from vendor A, if it's 160 pin, can be designed the same way as a QFP that's 160 pin from vendor B. But same you cannot say about BTC. You know, each same pin count, 160 pin, could be different. It will require different design depending on where this BTC is from. All right. So you have to look at the data sheet. Slide 15, this is an example of what we call discrete BTCs, not very complicated silicon and so on, but simple ones. And they are essentially, you know, just plain copper and simple package. Now on slide 16, one of there is a size of this. This can be very small, can be bigger than a dime and so on. But the thickness of the package, if you compare to the metal quad flat pack and so on, various types of packages, even the TSP, thin small package over time, and the BTC, they provide very thin package, and that's part of the reason their attraction into mobile devices of today. And speaking of mobile devices, on slide 17, it's a very fast-growing package, as you can easily understand, and the major driver is basically the mobile phones. Almost 3 billion people will have these smartphones and all kinds of phones. And if you open up any of these iPhone or, you know, the high-end smartphones, you get as many as 8 of these BTCs in each phone. And they are as fast growing as fine pitch BGA, also known as CSP, about the size of the bare chip, almost, just barely bigger than bare chip. And that's also very widely used in this mobile product. So there are some of these companies that are in business of projection and so on. So by the end of this year, which is just starting, they're thinking that maybe over 32 billion of these will be used worldwide, which is a big percentage of all these IC packages. So we are talking about a really, really high volume manufacturing process using these kind of packages. So very widespread uses of this package. So what is driving all that? Why? What is the benefit? Why is this widespread use? And the basic reasons are quite a few, as it is on the slide 18. It's excellent when it comes to electrical performance and thermal performance, because it's even better than BGA, because in case of BGA, those electrons have to go through the ball, and that's a travel distance that's involved. Not a very long travel distance, commute distance. So the commute time for the electron is less, and it just gets there from point A to point B in a much faster time. And that's what the electrical engineers call parasitic loss, which slows down the signal, and that's not the case in BTC. In BTC, you're going to have a much faster connection. And similarly, for thermal cooling, you are directly in contact with the board, so it's going to cool really well. And it's very easy to handle. Even if you drop this package on a floor, I mean, it doesn't have anything. There is no issue about bent leads. That's the main issue in QFP, because even, you can breathe on it. Depending on how hard you breathe, you may bend the lead and you got a defect. And you don't have that kind of problem with the BTC. So that's nice. Now, the big one here is, maybe not the biggest one, but at least right up there, is the cost. This is about a cheap package. To put this in proper perspective, if a package costs a penny, a US penny, a pin, is considered a very good price. Meaning, if any other device that's 100 pin and it costs a dollar, US dollar, then it is considered very good price. And I'm talking about the package, the housing cost, not the cost of the silicon inside, because that cost will be the same, doesn't matter what kind of housing it put in. But BTC is not even 1 penny, 1 cent. It's less than half a cent in some cases, and at least half a cent. So when it comes to the high volume application like these mobile iPhones and smartphones and those kinds of things, obviously half a penny here and half a penny there just adds up to a lot of pennies and millions and billions of dollars. And you add that to the excellent electrical and thermal performance, easier handling, I mean, you got a winner. So that's what's driving it, the cost and performance. Now, it's not without price. There is nothing is cheap, what it may appear. So the purchasing guy might be happy, but I think when it comes to manufacturing folks, like us here, the people who are dealing with the design and manufacturing, they are going to have to face all the challenges. And the concern basically is package coplanarity. So you don't have a lead coplanarity issue because the whole thing is flat, but the package itself, because after all it's a plastic package, and depending on how it's made, and so that may not be flat. And since you can put on a lot of paste, as the case that I suggested in the beginning, then there is not much of a way to compensate for the flatness of the package. And the only way is putting some paste, extra paste, then you'll end up having a lot of voids. And since there is no lead, there is a CTE mismatch issue. The package and the board, not the similar coefficient thermal expansion. So if you have a long shelf life, long life application, you got some concern there. And if these pitches of these BTC are very fine, you might run into the printing issue. If you have too much paste, it will start floating and cause a lot of voids. And if you have too little, then you got this opens and insufficient. Excuse me, what is this?
Sorry, everybody. It looks like Ray lost connection. I'm going to try to get him back on here as soon as possible. Just give me a few minutes. Thank you.
Okay, let's see. Is it asking me to do anything yet? No. Download what? So it should start in few. It says your webinar session should start in few seconds. Are you there?
Yeah, I'm still here.
Yeah. So it's. I don't know. There's anything for me to do here. It's. It's.
Okay, so your audio is starting to come over now.
So can you hear me on my audio thing on my computer through this? No.
I can hear you, Ray. I just
Okay,
can't
all
make
right.
you the presenter because it doesn't show that you're in the chat room here.
Yeah, so I don't see that. I just all right, let me get out again here. So I have the screen that came out, and I'm just sure you want to leave the seminar. No, I don't want to leave it. Yeah.
Sounds like you're in there now.
Yeah, I am now. I see the
Okay,
message.
Ray. I'm
Yeah.
gonna allow
Show
you to
my
pull up your
screen.
slides. Okay.
Yeah.
Sorry, everybody.
Yeah,
We're
okay.
having some technical issues here.
Okay. All right. So do you see my screen?
Yes, I do.
Okay. All right. So I think what I'll do is I think I'll just quickly go to slide 16. So I believe we saw that slide. This was working, right? Can everybody hear me?
Yes.
Am I on?
Yes. Looks
Okay.
good. I think we're back on track.
I think we are back. Okay, great. So 16 slide we talked about. I mentioned 17 about these very fast growing package with billions being used and it's very widely used, and that's what's driving it. And then I think I might have gotten disconnected on the 18. Do you remember electrical thermal performance? Did we get disconnected here? Hello? Can you hear me, Aaron? Aaron, are you there?
Yes, I'm here.
I'll just type the message here.
I'm here.
Okay, good. Okay, all right. So, do you remember the slide 18? You see that slide 18? Do you remember that I was on this? I didn't get disconnected here. Do you know
I
that?
believe so. I think we're right
Okay.
about here. If anybody knows differently, feel free to send me a message and correct me, but I think this is where we left off.
Okay, all right. Okay, so I will just go ahead and just repeat a few things. The basic thing, the driving, I think we were on this 18 around here. We got disconnected. So excellent thermal performance, excellent electrical performance, very low cost. Like I mentioned, it's the cheapest package money can buy, and that's what makes it an ideal package. So going on to slide 19. The major concern is that the flatness of the package and CT mismatch. And so it can be floating, it can be causing void. So that this overall savings that we have because of the lower package cost, it may not necessarily translate into the lowest cost. And that's what, I am on the slide, and this is where you call me that maybe we're not that we may have been disconnected. So just to summarize what we may have lost in last 2-3 slides is basically it's a very fast-growing package because thermal and electrical performance is very good. The cost is very low. But the concern is that it can create a lot of defects if you're not careful, and that any savings that you have in the package cost may not necessarily be realized if you're going to have problem in the assembly. So that's where we are. So we are all up to the same point. Now 21 slide here, just a nostalgic thing here. This is a package that used to be called a LCC, leadless ceramic chip carriers. And this is even before SMT became very popular. This is early 80s, late 70s. And now we have reincarnated this package. It has come up with a new name like BTC or micro lead frame and those names, but it is the same package that we had that caused us all kinds of problems. So just changing the name doesn't solve all those problems. So what you're looking at this package here is leadless ceramic that's gold-plated lead, and these are what called castellation on the side. So as a matter of fact, this was even a better package than BTC today because you can get the side fillet, because think of these terminations here where my arrow is as half of a hole that goes through the thickness of the package. So you are going to get a fillet, side fillet, plus you'll get this postage stamp as well. But these packages were made with ceramic, and now the BTC today, they're made of mostly plastic, but there are some of these BTCs that are made of ceramic. So unless they're very small, you still have to, the problem hasn't gone away. So if you have a ceramic BTC, be careful about the reliability of that package. And even when it's plastic, it's not the greatest. But if it's a ceramic, you're going to have serious issues, and no matter what the name is. All right? Now what we have on this slide 22 is basically what I just summarized so far in terms of the pros and cons of various types of packages. But this one sort of puts in proper perspective a Gullwing package, J-lead package, bottom termination package, and BGA package. And this is my summary of how to summarize these packages. So double circle here means excellent. Diamond is very good, good, and very poor. Triangle. So if I just go to compare these different features of these packages, compatibility with high pin count package, the Gullwing, is a diamond, which is very good, but it takes you like 208 pins. J-lead about 100 pins. BTC generally used for 100 pins. BGA, you can use for 1,000, 2,000 pins, 500 pins. So it's for high pin count. Okay. Package thickness, J-lead is the thickest one. BTC and BGA very thin. As a matter of fact, the BTC is even thinner than BGA. Lead rigidity, again, very good. Excellent for BTC and BGA. Gullwing is worse. Repair, rework, everybody is good except BGA is terrible. BTC is not very good, it's good. Not as good as some of the other packages. Electrical performance, you can see that Gullwing is worse and BTC is the best when it comes to electrical and thermal performance. And inspection, however, BTC is pretty bad, just like BGA. Ease of cleaning, that's a serious problem for BTC because there is no gap. And we will talk about in manufacturing what the issues are. You may have to make some major changes in your process just because of BTC. And package cost is excellent for BTC, is really bad for BGA. So, just to summarize the BTC column, you have excellent cost issue, thermal, electrical performance, rigidity, and so on. But bad thing is inspection and cleaning. All right. So keep that in perspective and compare that with other packages. All right. The manufacturing process for BTC, slide 24, it's done in various ways. So you're starting with a sheet of copper that you see here in slide 24. You can singulate it, cut it up with a saw, or punch it. And or there are times that this is substrate instead of copper sheet, a regular PCB is used as well as a substrate, not a lead frame. And so in that case, they singulate it because you can't punch a PCB. All right, that's how the packages are made. Now, slide 25 here, there is two kind of terms you want to get used to, and what is called pullback. And this is what the pullback means is that where this arrow is, the plastic is outside of the package, so you're not going to get a fillet. And so this is what on the top right is, so it can have 2 rows of wire bond and 1 row of wire bond. No pullback means the copper sheet is all the way to the end of the package, so you will sometimes, not always, get a side fillet. And that's what this thing is on the left. So there are 2 configurations of this. And this is showing in a different way that you have a die attach pad in the center, you have outer pin, there can be multiple rows like on the bottom picture, and they may have thermal pad, what they call DAP, die attach pad, or not. And in terms of the pin counts, you have the pitches 0.65, 0.5, even less. And these are number of pins. These are body size, outline how many rows and columns. Generally, they're used under 100 pins. That's where the BTCs are used. In slide 28, the pitches, they go at least maybe even 0.4 millimeter pitch. I will suggest that, probably not a good idea to deal with 0.4 millimeter pitch no matter what kind of package it is. There are some other studies that's when the defects the highest. You can have, especially in the gull-wing type package, you can really have high defect. But in BTC, not so bad. But anytime the pitch goes down, you have a problem. So if I have an option, I want to draw the line at 0.5. Obviously, when you have to use it, you have to use lower pitch. But what's interesting thing to see here is that this is the contact pitch, 0.65, 0.5, 0.4, and the nominal termination pitch, meaning on the PCB, is is roughly about half of that. And then you have to figure out how the dimension is. Excuse me, I misspoke. The pitch obviously has to be the same on the, they have to match. What I meant was the width of the termination, width of the lead is about half the pitch. In case of other kinds of QFP, the width of the lead is less than half the pitch. Like if it is a 0.5 millimeter pitch, the lead will be less than that, okay, width of the lead. But in case of BTC, it's about half in that neighborhood. So it's much wider than, the normal for other devices. Now what we have on slide, the next slide, which is slide 29, is a manufacturing process for the QFN. So you have a lead frame that's doing at a room temperature, and this the chat thing kind of hides part of the screen. Let me see if I can minimize that. I'll go there if I need to. No, doesn't do that. That's all right. So you take the lead frame, you dispense the die attached material, put the die on, and then you cure the die attached material. So now you have at 150 degrees C, a die is attached, and you have a mechanical connection. Now then you start doing the wire bonding of that, and you place the, once you've done the wire bonding, then place it in the mold, and then you are molding at this higher temperature, which is 150 degree, and now you are done with the bonding and so on. So remove it, and now you got one big mold, and you have to mark it, put the part number on. Now you start cutting him, chopping him up in small pieces. Singulate it or punch it, depending on what kind of package it is. Test it, and there you have done it. So essentially, that's the process and what temperature they are done at, and it gives you an idea about how the package is made. Another way to look at that is here you have on slide 30 the lead frame, which was one sheet of copper, then got etched, and the one on the right of it is each individual lead frame, and now you're going to put the die on it, wire bond it, then you put the mold on it, the middle picture, and after that you're going to basically chop them all up like a waffle pack, and each individual is in a is a BTC in a tray. And this is what you see, what's on the very bottom, and it's ready for placement in your pick and place machines. In a tray, it can be in a tape and reel, and so on. So the slide 31, when you're doing the saw singulation or punch, it's the lowest cost because it's done in high volume. You're just punching out hundreds of these devices at a time. When you have on a laminate, on a PCB, you cannot do the punching. You have to saw. You have to singulate it. It's very versatile process. When you have and on the PCB you may have more than one silicon. So it's what they call the system in a package. And they can be custom packaged as well, and people can get their customized package in less than 6 weeks, under $10,000. So anytime when you have consumer applications, not such a serious application, this is a package very widely used. LGA is a common for system in package. LGA is a land grid array with a lot more silicon inside, and they can have a resistor, capacitor, some other silicon, and from outside it looks like a land grid array, just one package. There are some issues with the package itself, package defects like delamination in the molding compound. That could cause the pulling the parts off the board, the substrate. I'm talking about the package here. If there's a mold compound flash that gets on the leads, or the termination, let us say, obviously that would be a problem with the soldering. So those are the kind of defects the package guys have to inspect and make sure they don't send it to you. There could be void in the molding compound itself that will cause the void in the package body. And then when the wire, there's all this wire bond inside, and if the temperature is not properly controlled and process not controlled, it could make those wire bonds inside, what they call the wire sweep, to move, and they will short inside, and they sometimes might even have wires that's broken. And those are the things that package guys have to inspect and make sure that you don't get it. So delamination could be caused during sawing the warpage can be caused during the molding process because that's inherent, and that will make the package not flat, and that will cause the solder joint issues. Sweeping of the lead, movement of those wire bonds will cause shorting and because of the high temperature and so on during the molding process. And QFP, even if they are small, generally they are not the moisture sensitive, but you have to check the data sheet because they can take a lot of water and cause the delamination during the reflow. So you have to treat them just like any other moisture sensitive package. So that's introduction. Let's talk about design. We are doing pretty good, and I'll talk about, and then we will conclude here in a short time. On slide 35, what you're looking at is a cross-section of a PCB, because this BTC and every other component has to get onto that laminate, to that board. Now, what you see here is plated through hole. That's a via or plated through hole. The difference between via and plated through hole is bigger. A lead goes through. A via is just for connecting the different layers. So this is connecting different layers. And the middle picture is just expansion of that. Now, what you see on the very right is the temperature, and y-axis you see the expansion. So every material, and we are talking about in here copper, essentially laminate, especially the epoxy that's holding these different layers together, will expand slowly up to its TG, glass transition temperature. And every material has a different TG, glass transition temperature. All right? And once that material reaches that glass transition temperature, it will expand at very high rate. So when you do the reflow at tin lead temperature, you have expansion from point here where my arrow is to the next line. But when you go to the lead free, you have this delta additional expansion where I'm going back and forth between these two parallel lines on the top of the picture here. So what that basically means is that if you take you are using whatever laminate for PCB for tin lead, and then tomorrow you start using the lead-free process with the same laminate, what you are going to do is you're basically increasing the potential that this via will crack in the laminate. So it's not the solid joint cracking, but the laminate cracking, the via hole cracking, and you have the same result just like solid joint cracking. So the solution to this thing is that when you go to the lead-free, and this has nothing to do with the BTC, you have to change the laminate material, which will add to the cost about 15 to 20% of the board cost, the laminate cost, not necessarily the board cost. And this slide 36 is basically explaining the same thing in a different way. You have on the left here, schematically, you see the temperature is at room temperature. Then when you go to this high temperature reflow for the lead-free, this laminate will expand and will stress these inner layers and cause the cracking in the laminate itself or cracking in the connection between the plated through hole or the via hole and the trace. So this is the trace, this is the via hole plating, and then you got a crack. And again, you got that problem of no connection, just like a solid joint connection. So the solution is making sure that you get a epoxy, or excuse me, the resin that goes into the laminate that's intended for lead-free process. All right. The other thing for the lead-free process is the surface finish. Of course, that has to be lead-free, but that has been lead-free for a long time, even before the lead-free came along, because of the flatness requirement. So you have, this is not unusual for just the BTC, but what's important here for BTC is, the options you have is Hassel, hot air solid leveling, you have immersion tin, you have a OSP, you have a ENIG process, electroless nickel immersion gold, and you have immersion silver. These are your options. So they are not all the options, but most of the prominent surface finishes, these are the options. So in this, the only one I would say that you should really not consider for especially if you have a BTC on board, is the Hassel process, and that's because of the flatness issue, and flatness is on the board itself because of the Hassel, plus the surface finish itself. In the hot air process, you don't really get a flat surface even if the board is flat. So that's one thing that is not a good thing. Obviously, none of the surface finishes are perfect. They all have their pros and cons, and I'm not going to go too much into the detail, but very briefly, immersion silver, starting at the bottom, has a micro via void issue. Sulfur is there in the environment that can cause the creeping corrosion. ENIG, the second one from the bottom, can have a black pad. OSP has some issues that has to do with the hole fill and how the surface finish is not very robust and may not be solderable for too long. Immersion tin is not a very solderable surface, and hassle has flatness issues. So they all have their pros and cons, but I mean, obviously you have to choose one of them, but the hassle will be one that you might want to stay away if there are BTC because of flatness. So this slide 38 is some kind of questions, I think, and answer in a different way, something that there has been some question in the past that whether there is any surface finish which is not good for BTC, and I answered that in the previous slide that I would say that hassle is not a good option. So you can go for immersion or ENIG, even some high temperature OSP. And then the second thing that do the BGA and BTC have the lower reliability while using immersion silver or ENIG for automotive applications. And again, BTC is not a good option if there is a potential for shock and vibration, and we'll see that in the second part of the presentation, but I just wanted to that if there is shock and vibration issues in the application, you might want to consider, it doesn't matter which surface finish it is, not to use it. All right. Let's get back to the land pattern design of the BTC, and then I'll open up for some questions. All right. Here in slide 40 for land pattern design. Now, as I mentioned earlier, the BTC footprint, whatever the pitch is, so you can see this, whatever the pitch of these pads are, the pitch will stay the same. And BTC footprint is generally is smaller than the pad, which is shown into the yellow. So the pad, and you should provide this pad extension, that's where I'm pointing at, where the arrows are, because you do get fillet at times, not all the time. And on the inside where the thermal pad is, so on the right side of it, you don't have to have pad extension like shown here. But for the first row, the outer row, you can have it. But if there was another pad behind it, like where this arrow is, if there was a 2-row BTC, then providing this extension is really a waste of space, because when it's hidden underneath, this pad extension is not necessary. So you could just make it a little bit bigger all around it for the inner rows. For the outer rows, you should provide an extension so you can get a fillet. And these pads, like I said here, they're a little bigger than the termination, extended for the toe fillet, at least the outer rows. And the other important thing is that you want to make sure that there's plenty of gap between the pad and the thermal pad. Outside pad, the signal pad, and the thermal pad, so that you don't have a bridging. And how much that is, that gap, minimum depends on the pitch, obviously, but also depends on the printer that you have. If you have a printer that costs over 100,000, I think you should have no problem, even if the gap is, close to 10 mil. But with the cheaper printers, I think bridging is a big issue. So you want to make sure that you have high-end printer, especially if you have fine pitch devices, doesn't matter which one. In terms of solder mask guideline as to how to do that, that's essentially no different for the BTC than it is for other devices. That's the position that we have taken at IPC, meaning there is a solder mask defined pad that you see on the right where the solder mask goes on the pad, and then on the left the solder mask stays away from the pad. So in general, the guideline that we have in IPC for BGA, for BTC, for anybody else, is solder mass should be non-solder mass. Pad should be non-solder mass defined. Doesn't matter what component it is. And so the one for SMD is not a good idea. And part of the reason is the copper etching process is more accurate, so you will have no chance of the solder mask getting on the pad, whereas the solder masking process is not that accurate. And in some cases like BGA, solder mask defined pads have even lower reliability, because where I'm pointing out where solder mask meets the pad, that's sort of like a ready-made crack, and it's not a good idea, especially for BGA. But it's not a good idea for any type of component. Now on slide 42, we are just basically showing that you have to obviously maintain the pitch that's on the pad, the same pitch that you have, and on the component, obviously. You are trying to provide pad extension. This is explaining in a different way. And inner pad extension is necessarily not necessary. So this is slide 42 is showing you that there is no thermal pad in the middle. Slide 43 is showing that there is a thermal pad. And we'll talk in the next class a lot of details about the printing and guidelines for those pads and so on. But for here, basically, this gap between the internal gap between the thermal pad and the land pattern should be such that we don't have a bridging. All right?
Excuse me, Ray, we have a question.
Yeah.
Why make the pad on the PCB larger than the BTC pad?
Okay, that's a very good question. The question is, why make the BTC pad larger? So I'm going to go back to slide 40. All right? So basically, the question is why this BTC component is this, and the yellow is the pad on the board. Why make it bigger? The part of the reason is that there's a that you don't always get a fillet outside, but there are a lot of times you do get a fillet. Sometimes these things are plated. Sometimes you have more aggressive flux that you're using. So if you had an extension, you'll get a fillet and you get added strength. That's the basic answer. The second one is for the inner rows where you are not going to get a fillet. And like, let's say I'm drawing on the right side of this for the inner row. There also we want it slightly bigger because you'll have a maybe component will shift during when you're plating. It may not be exactly on the money, so you have a little bit allowance for misplacement and so on. So that's the basic reason. All right. If there are follow-up questions, please let me know that as well. All right. So I'm going on to slide 43 that we talked about, slide 44. Now, just look at a little carefully in here. There's a lot of details, and so what I want to say is just read the pullback on very top. What that means is pullback component means that this is where my arrow is. That's a plastic, so you are not going to get a fillet. But what you do want is an example of a nice fillet here. You compare that pullback to the very bottom pullback, and that is not a good, this is kind of like a non-wetted kind of look. So this bottom is the same kind of package, the one on the top, but the top is an example of a good solder joint. Very bottom is, for that kind of package, pullback package, is an example of something that's not good. So you can also see the die attach pad, that this look is, you need to be totally whole thing covered. That's a good example. Now the one in the middle is the no pullback, meaning you should get a fillet. So if you get a concave fillet, obviously that's ideal. That's very nice by anybody's standard. But the one below, the third from the top, is an example of a bad, a weaker joint. And both of these, I'm not saying that these should be rejected, the one on the bottom, these two, but those are going to be not as good as the one that's on the top. Okay, so as some kind of inspection guideline. Now remember, you may not be able to see that all the time, these kinds of things, but when you set up your process and cross-section these things, that's how you can set up your process. Moving on to slide 45 and trying to set the stage here for how these things boards are designed. Now, you have, we talked about the thermal via, that how great it is, the BTC package, and that's good, but you need to have those thermal vias that helps in that process. So in this cooling, basically junction to case temperature, if you will, the lower number is better than higher number. So as you add more vias, the packages cool much faster, all right? And that's plotted again on this bottom picture here, that junction to ambient, junction to case, and so on. Those temperatures go down. The characteristic of the package keeps going down if there are a lot more vias in the package. So you do want those vias to provide that cooling. Otherwise, you're not going to have that. So, and anytime you have the void, in that thermal pad, obviously you're going to have the curve will be different. You'll have a different problem, and we'll talk about that as well. So the stencil design could be any of these things here, and we'll talk more next week. You can have a circular. Basically, what it is that wherever the white area is, the white area, that's where you are printing. Where the dark or gray is, you are not printing the paste. And you can have, these are examples of something like 37% coverage all the way to 80%. And what we generally after is about 50 to 70% coverage is what's considered a good spaced coverage. And we'll talk more later on. There are a lot of other ways to accomplish that. But there is no, specific pattern that's better than the other. There is a lot of discussion, and we'll discuss in quite great detail next week. Now, when you do have the thermal vias, how do you print it? Now, let's just go back to slide 48, and then we'll come back. Is that these are the, this is the inner thermal pad, and this is the via. So when you're printing paste, obviously you don't want to print it right there on the thermal via itself. So you have a clearance. So you're printing away from the via, and the basic reason is so the solder paste doesn't go on the hole. Now, one note here that is allows sufficient clearance around to prevent the paste from draining into the hole. And this clearance for lead-free can be a little bit smaller because the lead-free doesn't spread as much. It doesn't have as good a wetting angle that the tin lead does. Tin lead will spread out more, and then lead-free, that's part of the reason why we don't get a nice looking joint in the lead-free that we do in tin lead process. So, so when you go to this picture to the top right, top left, you can see this is what we're talking about. These are the vias, and that's shown in expanded way here in the middle. And we are saying that when you're printing the paste, make sure that you don't print the paste right over those vias. Otherwise, that paste will get into the hole. All right. I'm going to go back to 47 just to emphasize those points that you can lose the solder through those vias. And the other thing is that you can, when the solder paste does go through that via, it can create a bump on the other side, and that will cause some printing and placement problem on the secondary side when you do that side. Capping and tenting is used, meaning you can put some solder mask over them or inside the hole. Sometimes plating is done, plating it shut. But anytime you do the capping and tenting, there's a problem of sort of entrapping a chemical inside the hole. And if you are using, those chemicals, they're very aggressive, and they can cause the corrosion of the via. So you need to be careful when you do capping and tenting that there is no corrosive chemical inside those vias. So a lot of times people just get them plated shut, or they can also fill them up with a non-conductive epoxy, but that adds to the cost. So these are your options that we have on the top. The best way is just like we talked about in the next slide that we just did, that don't print the paste in the hole, just print it around it, so we don't have a problem on the secondary side for replacement, printing, and so on. All right, and drainage, because if we had drainage, we might have insufficient solder. Going back to slide 949, encroached via, but let me go back to the next slide to show you the picture, then I'll come back. When I'm talking about here is what is the definition on slide 50, the encroached via is that the green stuff here is solder mask, obviously. Here is the pad, there is the via, and we are talking about when you make the solder mask go over the pad. Now, this is different than a few slides earlier I talked about make sure the solder mask stays away from the pad. Now we are talking about, now I'm saying that, hey, for a rework, making the solder mask go over the pad is okay. So these are the pros and cons of this. But anyway, if there is a thermal vias, you are not going to be soldering those things anyway, and it might be helpful for rework that you let the solder mask go over, because you're not putting solder here anyway. This is just to hold that copper, during rework, hold it in place. And so the solder mask does not lift during rework. Going back to 49, that's exactly what I just said. So it allows the solder mask to, without, when you do the encroaching, it allows the solder mask, on the land without filling the via plated through hole. So it will hold it in place. A lot of other ways that you plate it shut, the via. So this is one way. This concept will permit any outgassing or cleaning of the via. So if this thing is open, it's still holding down the pad, but would let the outgassing go through, provide more surface coverage, and increase the adhesion with the mask and copper of that annular, what they call the annular ring, and it will hold it down. And that encroached via also gives you the larger web between the land and the via, so that's also minimize the lifting. So there is a, so all those are, they kind of add up to the benefit of, and that's a good approach. All right, and with that, we are back to the slide 51, and this is the handling of the moisture sensitive packages. What I want to say is that when it comes to lead free, and I have done a lot of audits in my consulting practice over the years, over the decades, there are very few companies actually that pass that. It's kind of interesting because this is one area that most people are not very careful, and I'm very thoroughly familiar with this process. As a matter of fact, I was the chairman when we created this committee that was in 1987, package handling. At the time it was called IPC 786, and these days it has been broken into two documents called IPC, not IPC, J standard. When people say, by the way, J, like J standard, like J lead, that's a joint standard by IPC and EIA. That's the JEDEC people that set the package standard. So there was a time that IPC will write a standard, and then JEDEC will write a standard as well, and they will be conflicting. And so we decided to have a surface mount console, and then we it started creating a joint standard so that the user gets only one set of standard, right? In any event, those when that was created in 87, and of course it has been updated in the form of J standard 20 and 33, the basic problem that happens, and most of you are probably very familiar, is that moisture, when it gets in the package, it will, when it goes through the reflow, that moisture will become steam, and that steam will crack the package. And that's why we want to make sure the package is dry when you're putting in the oven. And that job is done by the component supplier. His job is to bake it and put it in different labels, level 1, 2, 3, 4, 5, 6, and so on. And it writes down on the package that once you open the package, how many hours you have to use it before it takes on the moisture. There is a label in there that turns from blue to pink. So what normally you should do, there are a lot of ways to deal with it, that, you know, when you open the package, take out what you need, seal it back, and you know, you haven't started the clock for that. Or just have some mechanism that you open the package. If it's open during the day, then you have a running total that you keep track of. That if this was level 3, that means you could keep it open for 168 hours. And well, then you have to keep track of how many hours was it open in the meantime. So what really happens, most people don't keep track of it, how long they had it, and they're not even familiar with it. So this is why it's an issue. It's a simple problem, but you know, it's just most widely ignored or not followed. So what you have to do is make sure you have some procedure in place. And not all BTCs are moisture sensitive, especially the small one. And there are times that you can do the desiccation, meaning if it's been exposed for 8 hours, you can have it in a desiccant for 40 hours and it will take the moisture back. But that's about it. And a lot of time people think, well, we can bake it to recondition the package. That's really a bad idea, because every time you bake the package to take the moisture out, you are going to have, you're going to reduce the solubility, and it's bad enough already. I mean, remember, it was already baked by the component supplier one time. So if you have to bake a package, what that basically means is that you have failed in your process of handling the moisture sensitive package. So each baking is a signal that the process has failed, the handling procedure has failed, because ideally we do not want to bake, and we shouldn't take that lightly, especially we are using those no clean fluxes and this higher temperature reflow soldering, and you're going to create more defects if you have to bake it. All right. So the bottom line, again, to summarize, the BTC handling is no different than any other moisture sensitive package, but be very careful because these packages are very thin, and they could easily crack if they are moisture sensitive. With that, I think we have another 5 minutes or so that I'm leaving for questions, if there are any. And this is slide 52, and we will start this next week, same time, same place, and we'll be talking about printing, placement, you know, basically not so much as placement, but quality requirement, cleaning, which is kind of critical rework, and strategy for preventing the problem. So that's what we are. Just to summarize what we have done so far in terms of introduction, what we have talked about is that this is a very cheap package, very nice package, nice thermal electrical performance, but everything has to be perfect for you to have a good yield, because even though it's a cheaper package, perfection is not always possible in life, and whatever you save into the package cost, you may end up spending into manufacturing, which we'll be talking next week. In terms of design issues, you do have to, if it's lead-free, when we're talking about that, think of this as it's using a different kind of package that can handle lead-free temperature, and it's a moisture-sensitive handling of that is important. The laminate, you need to spend some more money in getting the PCB, that's the more expensive, so that they can take the lead-free temperatures. And in terms of design, the land pattern design is critical. The pads are slightly bigger than the footprint. The spacings needs to be critical. There needs to be plenty of gap between the thermal pad and the land pattern, so there is no bridging. If there is a via in the thermal pad, you want to make sure that there is a clearance between the solder mask and between the pad and the solder paste, so that it doesn't go through that hole. So those are the basic summary of what we just talked about. If there are any questions, we got about 5 minutes and we'll take that. So I'll turn this over to you, Aaron.
Okay, well, thank you very much, Ray, for your presentation today. At this time, I invite anybody who has any questions to submit them via the question box on your screen. As this has been a limited time for attendees to listen and follow along, we have encouraged you to send questions by email and be sure to use the Q&A forum on smta.org for continuing discussions, and also be sure to check the SMTA homepage for more in-depth resources and upcoming activities. Okay, so it looks like we do have one question so far.
Okay.
My chip is flip chip 40 ball. The pads are flexible substrate, is square shape. Similar to this BTC, the cross-section of solder joint always is not so good. Do you have any recommendations?
Okay, all right. So let me just read this interesting question. Please, one more time, just one more time.
Okay, let's see. My flip chip 40 ball. The pads on flexible substrate is square shape. Similar to this BTC, the cross-section of solder joint always is not so good. Do you have any recommendations?
Okay, all right. Okay, so this is...
He said 40 micron solder ball.
40 micron solder ball. Okay, okay, all right. 40 micron, all right, got it. Okay, now I understand. Okay, so it's like a BTC package, but ball is 40 micron, and it's going on a flexible circuit. So, all right, that's the question. So, to repeat the question, this is a flex circuit that you're mounting a flip chip package, which is 40 micron, and by the way, 25 micron is 1 mil, for those of you doing the translation. And so that's basically 1.5 mil, which is nothing. It's practically nothing. So he's correct in saying that this is just like a BTC. And when you do the cross section, you're not seeing much of a solder joint doesn't look that good. So what I would suggest depends on what the pitch is, because the ball is 40 micron. That means the pitch of this thing is very low. Now we are getting a different area here where we are basically have to figure out, you need absolutely the best printer money can buy. And I believe we are talking about, since I don't have other details about the pitch, what is the pitch of this, let's call it flip chip, which is like a BTC, if you will. And so absolutely the best printer money can buy, we are talking about a few 100,000 type printer, and try to get the most paste you can get, without causing bridging, of course, and you're pushing the limit, and that's all you can do. So you just have just try to print on the board, on that flex circuit, and that needs to be fully stretched. So application of the what is the most you can, and that's the only way that that cross section is going to look any better than it is. So, but by the way, this is not for everybody. We are kind of pushing the edge of the technology. All right. So in terms of the answer, that try to go for just go to the limit as to how much paste you can print. Go to the maximum just before you start causing the bridging. All right. And we are talking about particle size, powder size of 5 or 6 paste. If my assumption is right about the pitch of this flip chip. All right. Any other one?
No, I think that's all. Thank you very much, Ray. I appreciate it.
Yeah, and that questionnaire, you can send it the email with the picture and that kind of stuff as well, and we can take that up. If I didn't quite get it right, we can get it. We can address it again next week. that question.
Yeah, and if anybody has any questions that they think of afterwards, you can always send me an email. It's Erin, E-R-I-N, at smta.org, and I'll forward it to Ray.
All right, great, wonderful. This is 9:30 here on West Coast, and whatever time zone you are in. So have a rest of the wonderful day.
Yes, thank you. You too. Bye, everybody.
Okay. Bye.